We experience three dimensions: up, down, left, right, and forward, backward. But what if our universe is just a surface in a much larger, higher dimensional space? This is the essence of Brane Cosmology. Imagine a two-dimensional sheet of paper. To a flat creature living on it, the universe is only two-dimensional, a two-brane. Our universe, with three spatial dimensions, could be a three-brane. Brane Cosmology suggests our universe is confined to a three-dimensional brane, while extra dimensions exist outside it, in a space called the bulk. This explains why we only perceive three spatial dimensions in daily life. Like an ant on a lily pad, we might be unaware of a much larger reality surrounding us. Brane Cosmology challenges us to look beyond the familiar and imagine a universe far richer than we ever thought possible. If our universe is a three-brane, what lies beyond? Physicists call this higher dimensional space the bulk. The bulk is where our brain, and possibly others, exist, separated by tiny distances. All matter and energy are particles, visualized as open strings stuck to our brain. Gravity, unlike light, can move through the bulk, possibly linking brains. Gravity is unique in Brane Cosmology. It's not confined to our brain. The graviton, the particle that transmits gravity, is a closed loop of string, free to travel through the bulk. This leakage explains why gravity is so much weaker than other forces. Its strength is diluted as it spreads into extra dimensions. At very small distances, gravity could appear stronger, a prediction testable in high-energy experiments. If gravity can leak, so could the effects of matter on other branes. Perhaps what we call dark matter is actually matter on a nearby brane, felt only through gravity. This idea links the mysteries of gravity and dark matter to the structure of space-time itself. The standard Big Bang theory leaves questions unanswered. What came before, and what caused the initial singularity? The ekpyrotic model, inspired by Brane Cosmology, suggests our universe was born from the collision of two branes in the bulk. Instead of a singularity, the Big Bang was a dramatic event. Two branes collided, releasing energy and creating the hot, dense state of the early universe. This model explains the universe's uniformity and flatness without needing cosmic inflation. The brane's slow, parallel approach smoothed out irregularities. Some versions propose a cyclic universe. Branes collide, bounce apart, and eventually come together again, creating endless cycles of cosmic birth and rebirth. The ekpyrotic model replaces the mystery of a beginning with a physical, recurring process. It offers a radical new vision of cosmic history, one of cycles, not a single beginning. Brane Cosmology offers a new way to understand our universe by imagining it as a three-dimensional brane within a higher dimensional space. Matter and light are stuck to our brain, but gravity can leak into extra dimensions, which may explain its weakness. Some models even replace the Big Bang with a collision between branes, sparking cosmic expansion. Brane Cosmology could also link dark matter and dark energy to hidden branes and extra dimensions. Brane Cosmology is grounded in the mathematics of string theory and general relativity. In M theory, higher dimensional objects called D-branes are surfaces where open strings, representing matter and force particles, can end. The graviton, a closed string, is free to move in all dimensions, providing a mathematical basis for gravity's leakage. The Randall-Sundrum model explores what happens if the extra dimension is warped, curving space-time and making gravity appear exponentially weaker on our brane. This model solves Einstein's equations in a 5-dimensional, negatively curved space-time, localizing gravity near one brane and weakening it on another. These models make testable predictions, such as the existence of heavy Kaluza-Klein gravitons, which could be detected in high-energy collisions. The mathematics transforms Brane cosmology from pure theory into a scientific hypothesis. Experimental confirmation would revolutionize our understanding of the universe. The value of Brane cosmology depends on whether it can be tested. High-energy particle physics offers one avenue. The Large Hadron Collider could produce Kaluza-Klein particles, or missing energy, if gravitons escape into the bulk. Precision gravity experiments test Newton's law at sub-millimeter scales, searching for deviations that would signal extra dimensions. So far, no definitive evidence has been found, but experiments are pushing the limits. Cosmological observations also provide clues. The cosmic microwave background and gravitational waves could reveal signatures of brane collisions or extra dimensions. Competing models, like standard inflation versus the ekpyrotic model, predict subtle differences in cosmic background patterns. Future gravitational wave observatories may detect primordial signals unique to Brane cosmology. Each of these tests brings us closer to confirming or refuting the theory. The search continues, with every experiment refining our understanding. Brane cosmology remains a bold, testable idea at the frontier of physics. Brane cosmology has some big hurdles to overcome, mostly because we haven't found any direct proof for it yet. After years of searching, scientists still haven't seen any signs of extra dimensions or special new particles, and gravity still behaves just as Newton described. No surprises so far. The theory also needs a lot of things to be just right, like branes lined up almost perfectly, and it brings in some pretty complicated ideas that can seem a bit made up. Plus, no one really knows exactly what happens when branes crash into each other. So, it's tough to make clear predictions. Brane cosmology is also closely linked to string theory, which hasn't been proven either. So, a lot of scientists are still pretty skeptical about these ideas. Until we get some real evidence, Brane cosmology will stay an interesting but unproven way to look at the universe. Brane cosmology is a bold leap in our quest to understand the universe, suggesting we live on a 3-brane in a higher dimensional bulk. It offers elegant solutions to deep puzzles, like gravity's weakness and the nature of dark matter and dark energy, by connecting them to extra dimensions. The theory rewrites cosmic history, proposing the Big Bang was a brane collision, not a singular beginning. Yet, for all its allure, Brane cosmology remains unconfirmed, facing both experimental and theoretical challenges. It reminds us that our understanding of reality may be incomplete, and that the universe could be far richer than we imagine. Only future experiments and observations can reveal if our universe is truly a brane in a higher dimensional sea. Until then, Brane Cosmology stands as one of the most exciting and thought-provoking ideas in modern physics.